In the preceding section, we introduce an exhaustive infinite descent technique. This section aims to offer a more streamlined portrayal of this infinite descent-ascent process. The descent is executed through Fermat's little theorem auxiliary calculations, while the ascent is achieved by employing Edwards' method, just without the need of computing the residues. For clarity and ease of comparison, we will focus on the case of prime 1,299,841. So we see how the product of those equations mean that all prime factors but 1,299,841 are squared. So we can go the way up, finding the decomposition of them as sum of two squares. The product of 2 squared plus 1 and 12 squared plus 1 is divisible by 5 twice. So through Brahmagupta's identity, we can find which combination of signs let us divide by 5 both squares. There, we find that 29 equals 5 squared plus 2 squared. In the second step, 418 squared plus 1 is factored as 5 squared times 29 times 241. Remember, we just found the decomposition of 29, and the one of 5 squared is easily to find, 4 squared plus 3 squared. So we need to find only the decomposition of 241. So 25 times 29 equals either 26 squared plus 7 squared or 14 squared plus 23 squared. So using Brahmagupta's identity, we'll have a system of two equations with two unknowns. Using the same method to resolve it, we find out that A equals 15 and B equals 4. Thus, 241 equals 15 squared plus 4 squared. Next step is dealing with 31,507 squared plus 1. That's equal to 25 times 26 times 241 times 6,337. We already know the decomposition of 25 and 241. And the decomposition of 26 is easy, 5 squared plus 1. So we only need to find the decomposition of 6,337. To do that, we need first to know all 4 decompositions of 25 times 26 times 241. So we have 4 pairs of C and D to find out, and 1 pair gives the decomposition of 6,337. And the decomposition is 36 squared plus 71 squared. Finally, we reach the last equation, 462,779 squared plus 1 equals 26 times 6,337 times 1,299,841. And we know the decompositions of 26 and 6,337. So following the same procedure, we can find the decomposition of 1,299,841. 26 times 6,337 has 2 possible decompositions. So we have 2 pairs of combos for x and y, and only one is the solution. Solving the system of 2 variables with 2 equations finally show us that 1,299,841 equals 705 squared plus 896 squared. In conclusion, this method offers a simpler approach compared to the one outlined in the preceding section. It bypasses the need for use of variables in executing the steps and provides a faster solution. However, although the ascent steps are transparent and readily solvable, the descent parts still need the computing of Fermat's little theorem in each step, just like in the method outlined in the previous section, something that's quite tiresome when applied to composite numbers. In the following section, we will present a simple descent method that eludes the problem of doing multiple Fermat's little theorem calculations.